Hello, in this lecture, we're going to discuss continuous and discrete probability distributions. Outline: continuous versus categorical random variables, continuous probability distributions, discrete probability distributions. So we have just finished a measurement, and we know there are 4 levels of measurements that reflect how refined we want our measurements to be. And the 4 levels are nominal, ordinal, interval, and ratio. Some of the examples are people's age, which is numerical. A Likert scale is categorical, is actually ordinal. Racial background, categorical, is nominal. Employment status, nominal. Pain scale, usually an ordinal scale. And blood pressure, it's numerical. Continuous versus categorical variable. So a categorical variable can only take a set of distinct values. So their values can be separated. Okay, that's what distinct values means. A continuous variable can theoretically take any, therefore infinitely many values. So the value of a continuous variable is continuum. That means if you pick any 2 values of a continuous variable, you can always find a third value in between these 2 values. So that, in that sense, the value is continuous. So a random variable is a variable whose possible values are numerical outcomes of a random phenomenon. That means a random variable is a measure of an underlying random process. So it will take different values, and we cannot predict which value the variable will take. So we actually will assign probabilities to different possible values for this random variable. So continuous versus discrete random variables. Continuous random variables can take any values represented by real numbers. So if we want to distinguish between continuous versus discrete random variables, we can look at their possible values. The continuous random variables can only take values represented by real numbers. Real numbers are numbers with decimal points. For example, 3.18 or 1.05, these kind of real numbers. A discrete random variables can take a set of distinct values. They can be finite or they can be infinite. So finite, for example, cancer staging. So we have cancer stages 1, 2, 3, 4, for example. For infinite, we can think about the count data. For example, number of ear infections per year. So it can take values of 0, 1, 2, 3, 4, etc. Basically are counts. So, but they are infinite. There are infinite of those potential counts. So for discrete random variables, their value can be finite, but it can also be infinite. The probability is, roughly speaking, proportion of times an event is expected to occur in the long run. Okay, so that's a very rough description. It's not a strict definition. Intuitively, a probability should be between 0, which means never, to 1, and always. Okay, so here is a link to a video in Khan Academy about the concept of probability. So for a random variable, how do we describe its random behavior? Usually we try to describe we try to model the distribution of a continuous random variable. And for that, we can define the probability density function. It is used as a complete description of the distribution of a continuous random variable. So here I use the word complete. That means if we know the probability density function, then we know all the random behavior of this continuous random variable. So more mathematically, with a PDF f of x, the probability of a continuous random variable x to fall between any two values a and b is the area under the curve of f of x between a and b. So on the right hand side, you can see the graph. So the graph is the graph of the PDF. So given any two values a and b, you have the area under the curve in between a and b. Actually, mathematically, is the integral of f of x in a and b. That equals the probability for the random variable to take any value within a and b. Okay. So for PDF, here are some videos, including introduction of PDF and example of PDF. Please make sure you watch these videos. PDF properties. So first, range of possible probabilities must be between 0 and 1. Okay. And the sum of probability is the total area under the curve and equal to 1. That's called the total probability. Okay. The probability of x falls between two values is the area under the curve between the two values. And probability of a complement is equal to the 1 minus the probability of the event. So these are the basic properties for a function to be a PDF. Okay, and if a function is a PDF, it must satisfy these properties. So here's kind of a more mathematical way of describing the PDF properties. And next topic is how do we model a discrete random variable? Okay, the probability mass function, also called the PMF, is used as a complete description of the probability distribution of a discrete random variable. We can say a PMF is a mapping between all possible discrete values and their corresponding probabilities, what we call masses. So on the right-hand side, you can see this is a PMF for rolling a fair die. So the possible values are 1, 2, 3, 4, 5, 6, and each value has a probability of 1/6, to happen. Okay, so you can see that graphically what this PMF looks like. The properties of a PMF also, similar to the properties of the PDF. First, all the values of this function must be non-negative, and the total sum of all the possible values, the probability is equal to 1, and f of xi equal to the probability of x equal to little xi. So xi is one of the possible values. So the value of the PM function at this value equal to the probability of the random variable to take that value. And graphically, we can use a bar chart to represent the possible values, and the height of the bar represent the probability. So this is a complete description of the random behavior of a discrete random variable. Thanks for watching.